Okay, we go back to the op-amp. This one you already know that. Okay, we already done that thing here. Okay. And we already telling you, we get the op-amp just 3 terminal. Okay, one inverting, another non-inverting, and the output. Okay, you get a big resistance at the input here. So that's why just telling you the current cannot go to the op-amp. And you get the output resistance that is supposed to be a 0. So you can get the maximum current. Okay. And you can see this IC op-amp 741. Only 8 pins. Okay. And 1, 2, 3, 4, 5, 6. And that will be a number 8. Okay, if you get any question, just let me know before we can go to the new thing. Okay, and this one, that help you to read it, to understand it. Okay, and we done on that thing. And yesterday we already talking about that open loop gain. The open loop gain, the bandwidth will be very, very small. In this case, they get only 10 Hz. Okay. So in order to get a more bandwidth, then you need the feedback. Okay. When you get the feedback, they will be reduced the gain. However, the bandwidth will be bigger. Okay. And this is an inverting amplifier. First thing, the input will be applied to the negative. Okay. And the output of the op-amp here, we already know they will be inverted of the input for the sideway. Input output will be 180 degree out of phase. That means they opposite. Okay. And the resistor RF here, that means the resistor connect from the output back into the input. Okay. And we already know VD, that means the voltage difference between V1 and V2 will be equal 0. That only telling you V1 and V2 will be the same. In this case, V1 connect to the ground, 0 volt. So V2 at that point will be also 0 volt. However, they get a special name, a virtual route. Okay, this is a physical route. That means you need a wire connect from input V1 to the route. However, on the V2, the point right here, they not connect direct to the route, but they still 0. Okay, so that's why they call it virtual. So the current going from V in go to R in, and they cannot go to the op-amp. They will be go through RF and go to the output here. However, the output here, you can get a negative side here. So current cannot flowing down. They will be go inside op-amp. In this case, we call a sink current, op-amp sink current, okay? Current go into the op-amp.
Mr. Pham, question?
Yeah.
On a V1 and V2, are the voltages the same then on that circuit? Do
V,
they try? Does the V1 and V2, the differential, do they try to keep the same voltage?
yeah, the thing is the difference is 0. So that's why V1, V2 the same.
But when the current flows back in from I out to V1, it's always going to remain 0, or it's going to try and cause the inputs to retain their voltage, a voltage value, instead of being 0 on that circuit. If I apply 1 volt, will I get a
You,
1 volt?
you get 1 volt in here?
Yeah, well, if I apply 1 volt to the circuit, I'll still get 1 volt at V2 and V1, right?
No,
Because of
V2 and V1, the difference have to be 0.
thank you.
You understand that the current go into this point right here, they're not going down. I think a negative on the IF right here. So they go into the op amp, basically they will be put to the route. So that's why they call a sink current, okay? And also we already calculation for the gain. The gain will be minus RF divided to RE. So what you need to do, when you look into the circuitry, you have to know that will be inverting, I mean, op amp. And also we need to know what is the gain. The gain will be equal minus RF over RE. Okay, that's a key point we have to know.
Mr. Pham,
Yeah,
going back there, I've got a question. Fee in, when it go in at fee in, which is, yeah, at that point, whatever voltage would go in, it'll go past that virtual earth
yeah, yeah,
point.
right.
So, I mean, if that is 0, because V1 is grounded to 0, then X should be 0.
Right.
So how is that,
That's
fee
why.
in?
That's why the claim of virtual.
Uh-huh.
Current can be flow through.
So current still go through, but then we're saying the voltage is going to be 0,
The voltage is 0.
even though it's going through R in, the resistor R in.
Yeah.
There must be a voltage going through there.
Yeah, the voltage still go through here. So that's why this is a routed.
Uh-huh.
So that's why you can calculate the I in equal V in divided to RE.
Okay. So in that case, that means RF on the left-hand side, the voltage is 0 then.
RF here?
Yeah.
IA 0, correct?
Yeah, it's 0. And then the right-hand side could be plus or minus whatever voltage it is.
Right.
Okay. All right. Thank you.
Mr. Pham, so for that example, there is only 0 volts in, only for that example, 0 volts in.
0 here?
No, to the left.
Here?
Yeah, right there. Yeah, right there. So there 0 volts are going in right now instead of.
No.
They just given, V in, they not given you the value.
It's not 0 V in.
Yeah,
There's a voltage going in, but then once you go through the resistor, the voltage drop to the 0 at point X.
Right.
That's the potential drop.
Right, but that went along with my question. If you applied 1 volt, the stability of the differential, whether, because it technically the circuit's supposed to keep the voltage in as part of like a feedback. It's supposed to stay voltage in at V2 and V1 at 1 volt. If you send one in, it's supposed to kind of be fed back, and V1 and V2 stay at 1 volt.
No, it'll be 0.
No, but all right, go ahead. Because of feedback right there. So that it's just trying to clarify that sync drop right there.
Okay, make sure you understand it is a 0 volt. Okay, and this 0 volt different from this 0. So that's why they get a virtual route. Okay, a route current still flow through it. Okay, now you can see that virtual route here. Okay, so in this case, you get a 5 volt current go into that point here, do not go inside. Okay, they go up. okay? And when they're going up here, go through RF will be positive, leaving will be negative. So if you get a negative here, then you get a negative here. For RL, you get one side negative, the other side must be positive. So the current I going down here, they cannot going down. The thing is, current have to be flowing positive to negative. So that's why current go inside the op-amp. In this case, we call it sink current. And also you get a current IL going from 0 here to the negative, and they also go inside the op-amp. Okay? That's what,
Mr.
yeah.
So current,
Mr. Fan, once the current go in, where you got V out at, the current goes into the op amp. Once it get in the op amp, where does that current go? In other words, I'm trying to figure out how the current cycle.
Oh, they go inside here.
but the
And
current,
then,
Black box.
and then
Normally,
whoa, whoa.
it will go to the route,
it goes inside the op amp and then does what?
to the route.
Go to the ground.
so the ground at positive flows the ground, current flows the positive ground, but it does not go back at inverting to make a loop.
No,
So it pulls straight to ground.
who know what's going on inside?
Okay.
Okay,
It's black box.
for sure.
But then the DC is still helping the circuit. I mean, excuse me, the DC in to power the amp. That's keeping the current flow.
Right.
So Fam, I have a question about the amplification side. So if we have the I out is the sum of the I plus IL. So the I out is the amplified current. How do we use this amplified current in outside, like with other circuits, like with loads, like for example, if we have a speaker and we would like to have amplification of the voice, how do we connect the V out or the I out into the outside circuits?
Now that's what you connect into the load, that's outside.
But this is just like one current. It's not sum of two currents, which means this is not amplified.
Inside here, and this one also go inside here.
Okay. So I'm talking about the math. Like the math shows that the I out is the maximum current, which would be the amplified current.
Now,
That should be used on the load. So in this case, if we're looking only on IL,
right.
it's just a single current. It's not amplified. So how does the amplification happen in this the case for the load?
Now depending on what they need. If you want current out, then that's why you can get the current I out go this way.
That's the question. How do we get the I out to the other way?
Non-inverted.
I'm sorry?
That will be a non-inverted.
Non-inverting. Okay.
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 Basically, depending on the purpose, they need to inverting or they need non-inverting. If they want to draw the current go to the op amp, they must be inverted.
I see. Okay. Thank you so much.
Yeah.
So, Mr. Pham, so with that example, at V out, that current always stays in that loop regardless of the load that you connect at out.
Exactly.
That current will never redirect itself to the larger load resistance.
No.
So, all right. So going along with what that gentleman was saying, in order to gain in order to use the gain, it's all relied as far as the component at RL that's going to use the gain. RL is the only thing that's going to use the gain.
Right.
So if that resistance is increased, or excuse me, if the resistance is lowered, I get more gain.
Resistance on the load will be increased. What do
No,
you mean?
if I reduce the resistance
They're not getting on the gate.
on the load, but if I reduce the resistance on the load, I get more gain.
No,
So because I'm what
the gain will be a minus, in this case, minus R3 over R1. Nothing to do with the load.
well from what I understand, the op amps is just supposed to have infinite gain, correct?
Yeah, but the thing is, depends on what the purpose. Okay, if you want the load here got more current, then you have to using another one, not this one.
Right. So it's specific to purpose and use. All right. Thank you.
Okay, so now for that one here, okay, they will be inverted. The thing is they connect to the negative. You want to calculate the gain, you take minus R3 divide R2. Okay, and if you want to calculate the V out, then V out will be equal the gain times V in. If you want to calculate the load current, you take V out divide to R5. Okay, and if you want to calculate the current I, we already know I. You take the 1 volt divide to 1K. That's what on the example here. Okay, and also bring it up on this thing here. They apply the AC. So the gain you can see, you get minus 4.5 divide 1.5. Okay, if you want the output, you take the input times the gain. However, we're not using the minus sign. The thing is a sine wave, AC. Okay, input, output, when they get a minus, they just opposite. Okay, output will be a negative, input positive. Okay, 180 degree of phase. That's what we already done. Okay, now that will be non-inverting. When you see the input apply to input positive, that means non-inverting. However, this is you get a V1 5 volt, but not the inputs. Input have to be right at the input positive. That means at this point right here. Okay, in order to get a voltage here, you're using voltage divider. Take 5 times 1K divide 1K plus 1K, you get 2.5K. Now, the difference between the positive and the negative will be 0. No difference. So that's why if you get a 2.5 volt here, then also you get 2.5 volt at this point. No route, okay? No virtual route. The thing is we don't have a route right here. So if you get a 2.5 volt here, and this is a route, you're able to calculate the current I. You take 2.5 divide R1. You get that current. Basically, that current will be coming out from here. Okay? And this current going to here, they cannot going down. Okay? They go into R1. So, after we do a calculation, the gain for the non-inverting will be equal 1 plus RF divided to R1. Okay, that is the gain. If you want to calculate the voltage V out, that means the voltage measured from the output to the route. However, this is the load, cannot be using formula. So now V out in here, you can see, we can go from here to here and this route right here. So V out will be equal the voltage drop across the RF plus across the R1. Okay, so that's what you can calculate the V out. After V out, you can calculate the IL. Take the V out divide to IL. That's what you get the IL. Okay. That one also yesterday we already done. Only one thing, the gain of the non-inverting all the time have to be greater than 1. The thing is ACL equal 1 plus RF over R2. So they must be greater than 1 all the time. Okay, now this also, when you're looking into this circuitry, try to recognize that will be non-inverting. Okay? The gain will be equal 1 plus RF divided to RI. If you want to get V out, to take the gain times V in. Okay? And then they can ask you the current go through this 10 kilo ohm. So you understand V in here, they given you 2 volt. This 2 volt here, then that means you get 2 volt here. So you get a 2 volt at this side, a ground on the other side. Then the current I equal 2.5 divided to 10K. That's what we done yesterday. Now, that one. Okay, who can get through that one? What are F equal? They say the determine value of RF required to produce a closed loop gain. Okay, of my minus 100.
220 kilo ohms.
We'll see. Let's see, I can calculate right here. Okay, you get let's see, gain ACL equal what?
Negative 100.
Minus 100, right?
Yes.
Minus 100. And they will be equal what? That will be a non-inverting, right? Equal minus RF divide RE. Okay? And now what they want? They want RF. So what RF equal?
220
Negative.
kilo ohm.
Okay?
Negative 100 multiplied by 2.2K.
So that will be 100, right? Divide, right?
No, multiply.
It's multiplied.
Multiply by RI, right?
Yes.
Okay, time. Okay, RI. So they will be equal 100 times 2.2.
220.
220 kilo ohm.
Okay, so you get what, 22 or what?
220 K.
2.2 times 100. 220K, right?
Yes.
Okay, K ohm. That was easy one. Okay. Any question?
Yes, Mr. Pham, the value, the negative value, the minus 100, the minus is because this is an
Now,
inverting
both
amplifier.
minus they cancel.
Again, please.
Minus 100 equal minus here. So they cancel out. Resistor value cannot be negative.
Yeah, I understand. But what is the meaning to say that the amplification is the gain is a minus 100?
What do you mean for minus 100? What's wrong with that?
What does it mean? A minus 100 of gain. The gain is minus 100. What does it mean? The negative number associated to that amplification.
The input signal and the output signal are out of phase, 180-degree phase difference.
That's only telling you they will different 100 times in the upper, more or less. That not mean you apply 10 volt, you get a 20 volt. That's the gain positive. Also, you can get a volt negative. Okay? You can get a input bigger, but the output will be smaller, a 28.
Okay, thank you.
Yeah,
Thank you.
it don't have to be. All the time have to be higher.
Got it. Thank you.
Yeah. Okay, unity gain amplifier. You see that one here, they connect output to the negative, no resistor. Okay,
Subwoofer.
then now they get how many different name? They get a different name, buffer amplifier, isolation amplifier, and a follower. Okay, what is the gain for this amplifier?
One.
One,
The thing is input 10, output 10. You don't have any resistor here. Okay, gain equal 1. Output input will be the same. Why we need this amplifier? Okay, now,
So
yeah,
isolate one portion of the circuit from another portion of the circuit.
they isolate between input and the output.
Yeah.
The reason they get a big resistance inside here. So you can see the application in any power supply. They will get this circuitry. Okay? The thing is when you're doing with the output for some reason, you short it to the route. Okay? Without this amplifier, they will be cook your circuit. Okay? The thing is when you short it to route and the input still okay, the thing is they isolate it. Okay? So normally you're working on the lab, you short the 5 volt to the route. You don't have any more 5 volt. However, if you remove the short for a while, they going back. Okay? Without this amplifier, they will be cooked your circuitry. Okay? They will be burned in the power supply.
Mr. Fan.
Okay? That's the isolation and the buffer. Okay? And follower, that means input, output, follower.
Mr. Fan.
Yeah.
Isn't that connection from V out to negative mainly just to keep the amplifier stable at the input voltage? So if whatever goes in, if it's measured, if it go whatever goes in, that connection right there keeps the amplifier stable at whatever voltage it goes in because of negative feedback.
Yeah, negative feedback doesn't matter. They just telling you whatever come in, they come out.
But doesn't the amplifier work to where it has to keep both the input and the output? I mean, excuse me, has to keep the positive and the negative inputs the same, right?
Positive and the negative will be the same. The difference will be 0.
But but just in all amplifiers, isn't the inputs always struggle to stay the same? Isn't that the purpose of the amplifier, is to keep the inputs the same?
That is the basically purpose that they try to get input output the same. However, they must be isolated. You get 10 volt in, you get 10 volt out. You can understand 10 volt here, you go in here, the difference is 0. So that's why you still, both will have to be the same. Whatever you change in V in, V out will be followed. However, they not connect together. So that's why you get a problem with the output here doesn't have, that not happen to the input. Input still be okay. That's the main purpose of the follower or buffer amplifier. Or they say isolation. That means they isolate between input and the output. Okay, next will be summing amplifier. Okay, you can see now they're using inverting. However, they get not only one input, they get a V1, V2, and V3. Okay, and R here, that means the RF. That's what they call a summing. So in order to get the output, V out, they could be equal minus V1 plus V2 plus V3. You get more, then keep adding up. Okay. Now, try to see what we say here. Different amplifier. So in two input circuit, that amplify the difference between V1 and V2. V1 is connected to the inverting side of U1. V2 connect to the non-inverting. Okay. When R1, R2, R4, R5, 1, 2, 4, 5, the same value. The different amplify subtract V1 and V2. That means you want to calculate the V out. V out equal V2 minus V1. Okay, that's a differential amplifier. That means input applied to both positive and the negative. They're not inverting. Okay, they're not non-inverting. Inverting, non-inverting, they apply only one input, and this is a differential amplifier. In practice, the input impedance for V1 equal ohmic value of R1. Input impedance V2 equal ohmic value R2 plus R4. Now, if you're looking into here, okay, the voltage to U1 is not the V2 right here. They have to be right here, right at the positive, okay? If you want to get the voltage at the right positive input, you must using voltage divider. Take a V2 times R4 divide R2 plus R4. A different amplified circuit combine the gain effect from the inverting and a non-inverting, okay, resistor ratio. So if you're looking into here, okay, now, my question is, if I rounded positive, rounded here, what is the name of the amplifier?
Inverting.
If I rounded here,
Inverting amplifier.
Inverting amplifier.
inverting amplifier. Can you tell me the gain?
I'm sorry, what's the question again?
Can you tell me the gain when you said theta in inverting?
R5 divided
Negative.
by R1.
Negative R5 over R1.
minus R5 over R1. Correct?
Yeah.
Okay, now, if I rounded V1, I rounded here. What is the name of the amplifier?
Non-inverting.
Non-inverting. Correct. What is the name for non-inverting?
1 plus RF over R1.
I don't care F. I don't have an F here.
R, R,
You say that there will be a non-inverting, correct? But I want to know the gain for that non-inverting.
1 plus R5 divided by
5 over
R1.
R1.
Correct. 1 plus R5 over
R1.
Okay. The thing is, when you're solving the problem for differential amplifier, you cannot solve at the same time. But you have to round it V2 to calculate the V with the input V1. Then you have to calculate the input V1 to calculate the V2. And now you already know what the configuration, and that will be here. Okay, now for V1, VL equal, okay, for V2, VL equal, okay, that is the thing for the input V1, they will be inverting. So VL equal V1 minus V1 times R5 over R1. That is the gain. However, if they want to calculate the V2, then you see that they have to be V2 times R4 divided R2 plus R4. They must be get the voltage right here, not here. Then you multiply by the gain. Gain will be 1 plus R5 over R1. Okay, now you do it for me. To select A or B or C. If V1 and V2 equal 6 volts, then what VL equal?
Should be 0 if this is a differential amplifier.
A or B or C?
B.
B.
Oh. But wait.
Okay, so basically, if you get a 6 volt here,
I say C, 50-50.
okay,
No.
if you get a 6 volt here, VL will be equal
-6.
minus 1 times 6, right?
Yep, -6.
Negative 6. Then now if you get a 6 volt here, the voltage here, VA here, supposed to be divided by 2, 3 volt.
3 volts.
3 volt and time the gain, okay? The gain will be 2, right?
The gain is -1.
Come on.
Yeah, because
Sorry. Right now I using V2.
okay, I'm sorry.
So they will be 1 plus R F divided R1. That means gain equal 2. 2 times 3, 6 volt. So you get a 1 negative 6 volt, 1 positive 6 volt. Output will be 0. In order to easy to recognize which one output, is correct, A or B or C. I can tell you easy. You know for sure here, point A here, have to be 6 times 10 divided 20, 3 volts. So only the answer will be C. For that one, answer will be C. See that? C. That's the correct answer.
So when I did 50-50, I was right, Mr. Pham, huh? Good guess.
You were right, Mr. Joseph Smith.
Yeah, good guess.
The thing is, when you're doing your left vote, you can see this again. Okay? When you see any picture look like black and white in here, that's coming out from left vote. Okay, now you get the V input here. Okay, in this circuit, the sideways generator apply an unwanted common mode input voltage. That's a common mode to both input to both circuitry inputs. Due to the common mode rejection of E1, sideways does not appear at the output. Okay, the thing is both input will be the same, output will be cancelled out. That's what they're talking about. Common mode rejection ratio. Common mode input voltage appear across inverting or non-inverting input of different amplifier across both input of the different amplifier. LB.
B.
E.
The thing is number 1A, they say across the inverting or, no, not all, have to be both. That's what they common. Answer will be B. Okay, common mode rejection ratio CMRR is given in dB, measure the ability to cancel or attenuate, reduce common mode voltage. The amplitude of the unwanted signal appear at the circuit output V out CM equal AV over CMRR times VCM. CMRR must be converting from dB form to the numeric form. VOCM is the remain common mode input signal appear varying at the amplified output. Okay, in this different amplified circuit, our resistor R1, R2, R4, R1, R2, R4, R5 are made equal to each other. Due to the resistor value Vout equal V2 minus V1, or the difference between input voltage, that's what they are already talking about. Okay, output voltage polarity determined by the relationship between non-inverting input voltage to the inverting input voltage. The V2 polarity dominate the V1 polarity and determine output voltage polarity. Now, in this circuitry, consider V2 more positive than V1. Output voltage polarity A negative, B positive. Which one?
Negative.
Yeah, A.
It's inverting.
Consider V2 more than V1. Output voltage polarity
Oh, then B. Yeah, I'm sorry, B.
polarity I supposed to be following V2. B. Okay, in this case, sometimes, in the left phone, they asking very, very basic question. Carry me LB.
A.
Hey, okay. That means, very, very basic. Hey, I never asking this one. Okay, now the following relationship apply E1 is not saturated to the circuit cell. VL equal V2 minus V1. VA voltage divider. Okay. V2 times R4 divide R2 plus R4. VD equal 0. And VA and VR equal VR4. That means whatever voltage here and the voltage here, they will be the same. That all we already get it. Now, in this circuit, S1 is used to switch V2 or V1 into the circuit VR. A vary between B essentially 0 for either S1, vary between 0 and minus 10, both A and C, depending on position of S1. So if you see in here, this is the switch there. They can go in here or they can go in here. Okay. So what they want to see V out, A or B or C or D.
B.
You say D,
B.
B.
Yes, sir.
Okay, you say essentially 0 for either S1 position.
Yes, sir, because both voltages still connect to both inputs.
Perfect.
D as in David?
No,
That-
B is in boy.
Yeah, perfect. The thing is, no matter what, the switch here connect to V2, both input V1, V2 the same, right?
Yes.
However, input here, okay, and the same, and you say B, correct? Essentially 0 volt for either S1 position. The thing is that will be a common mode, right? The thing is they get the same voltage, so the output have to be 0. Okay, the difference between amplifier combined input waveform and account for amplitude and the phase. If R1, R2, R4, R5 are equal, VL equal V2 minus V1. You can see the thing here. They get E1, V1 and V2 both are sideways. However, this sideways must be opposite. You see that? One going down, the other going up. If they the same, they will be 0 out. Okay? They must be different.
So the output took on the same as V2.
What?
So the output waveform is the same as V2. Is
Now
that
it's
what
not the same. You have to do calculation.
oh, okay.
Okay? However,
Okay.
I emphasize here, input must be our phase.
Mhm,
Okay.
okay.
If you get the same phase, output will be 0. Now, you can see that one, identical, right?
Mhm.
If V2 and V1 are identical, in amplitude and the phase, we are essentially 0. did occur when R1, R2, R4, R5 are equal in value, or when the ratio R5 over R1 equal ratio of R4 over R2. Vout is 0 because of common mode rejection capability of U1. Okay, now, based on the circuit information, what Vout, you do a calculation for me. V1 equal V2 equal 2 volt, peak to peak. And they want to know what is the Vout. In order to do it, again, I already telling you, you have to round it V2, calculate V1, inverted. So output V1 out here will be equal minus 10, divide 10 is minus 1, okay, times 2 volt. Okay, so basically they will be inverted, okay? And in order to calculate the V2, you round it V1. And you must calculate the voltage at this point right here. 10K, 10K. And the 2 volt here, you get a 1 volt here. What is the gain for V2? If you calculate the V2, that means for none in,
Oh, is it 1 plus 1 over 1?
right, 1 plus 10K divide 10K. That means the gain equal 2. Okay, so which one, A or B or C or D is correct? Calculate, tell me.
A.
You say A,
A.
okay? The guy say A.
Yes.
Anyone get a different?
C,
You say B,
E.
A, C. That means you say 4 volt, right?
Yes.
Okay. One said 2 volt. You said 4 volt. I want to say what they said. Answer will be 4 volt.
Thank you.
Yeah,
Oh, so Mr. Pham, so you have to add, so we got 2 for V1 and we got 2 for V2. So you add them both up and is that how you got the 4?
right.
Okay.
Doesn't the circuit work as a comparator?
Now we're not comparing. That difference on amplifier.
Next.
Yet. And oh man. So that look like cover most of the thing for op amp. Okay, I believe you guys will be doing good on the op amp. Will be get more assignment on the op amp. Okay. Any question on the op amp?
Now filter.
If it's not, then we can go filter.
Good job, everyone.
Okay. Let's say I stop sharing that one. Okay. And now I share on this side here. Let's see. Okay, now we're talking about the filter. That means we'll be talking about the frequency domain. So on this sideway, okay, and you can see how do we calculate the period t. That means from here go to here. That will be one period. If you get a period, you can calculate the frequency f equal 1 over t. And the same thing, you can see the sideways. Okay, one period here. However, that is for the distance. Okay, that is for the distance, not the time. Distance here. That means the lambda here, they call a wavelength. And lambda will be calculated equal V divided to F frequency. And V equal 3 times 10 power of 8 milli per second. That's the speed of the light. Okay, and F will be in hertz. When you're learning for RF radio frequency, we deal with the lambda. Okay. Now, you get the amplifier, the gain equal to 1. You get input 10 volt, then you get output 10 volt. That's easy to recognize. Okay. And they're going to know what AVDB equal. You take 20 log of 1 and you get 0 dB. 0 dB mean what? Mean no loss. If you apply 10 volt, you get 5 volt out, you get loss. Okay? So if you get a 10 in, 10 out, that means the gain equal to 1. You take the 20 log of 1, you get a dB. Only thing you make sure you understand is decibel. That means you get no loss. Okay? Now, at the critical frequency, what is the V out? You understand at the critical frequency, output going down to 70.7%. Okay? That means if you get a 10 volt here, you want to get a V out, you take V in 10 times 0.707. That's what the output now will be 7.07 volt. Basically, you get loss. What the V out at minus 20 dB. So 20 dB, you understand that will be a 0.1. Okay, you take the 10 volt times 0.1, you get a 1 volt. Okay, that is the way. How do we calculate the V out? If they lost how many dB? Okay, if they lost a minus 3 dB, you know, you take input times 0.707. If they say they wanted minus 20 dB, that means 20 minus 20 dB is 0.1. You take your 0.1 times 10 volt, you get 1 volt. And now if they say I want minus 40 dB, that means 40 dB will be 0.01. Okay, and so on. Again, try to repeat that one for you. This is a sine wave. Okay, and this will be square wave. So basically, you can say square wave will be make it up by the sine wave. The sine wave, they get the first thing, they get a fundamental. And the next one will be first harmonic, second harmonic, third harmonic. That means a different frequency sine wave. And they combine it, they make it up the square wave. If I say I get a 1 kilohertz sine wave fundamental, what is the third harmonic frequency? What is the third harmonic for 1 kilohertz?
Derivative, I think.
What is the third harmonic?
The third harmonic is 3 kilohertz.
3K.
3K.
Yes, sir.
Right, correct. 5 harmonic.
5K.
5K.
Okay. 7 harmonic will be 7K. Okay. The thing is they're using the odd harmonic, they're not using even. Even means 2, 4, 6. Okay. Now, another question. If I get a 1 kilohertz sine wave, what is the bandwidth? What is the bandwidth for 1 kilohertz?
F1 and F2.
Okay, basically the bandwidth will be the different frequency, right?
Right.
Okay, the general formula, bandwidth equal F maximum minus F minimum.
Minimum. So it should be 0.
Perfect. Why 0? The thing is you get a 1 kilohertz sine wave. That's only 1 kilohertz. You cannot get any different. So that's why on the oscilloscope, when you see 1 kilohertz, you can get only 1 kilohertz. You cannot get another. So F maximum, F minimum will be the same. Okay? So the bandwidth of 1 kilohertz will be 0 hertz.
Hey, Mr. Pham.
Yeah.
Did you or did you not in the past say that something around 11 or either 13 harmonics will give you the pure square wave?
Yeah. However, if they asking you what is the bandwidth for 1 kilohertz square wave,
Then I'd say maybe like 11.
so basically, when they asking you what the bandwidth of the 1 kilohertz square wave, and you know what is the minimum is 1 kilohertz. However, you don't know what is the maximum. So the question is, you have to ask them, okay, you want 1 kilohertz square wave, but what harmonic they want up to? If they say, okay, I want up to 3 harmonic, so now what is the bandwidth?
2.
2K.
2K, that means 3 minus 1. Okay? Most of the things happen a technician, you will be doing calculation up to 13 harmonic only. Okay? They don't want that anymore. Okay, now you see in here, they display a square wave in the oscilloscope. Okay, 1 volt means 2 volt, peak to peak. Okay, and frequency 1K. And now, if you display in this is the time domain T, on the other one is the F frequency domain. They will be displayed on the spectrum analyzer. A spectrum analyzer for 1K square wave. Okay, this is a fundamental 1K here. And they not display for the even harmonic. They display odd harmonic. Basically, they just telling you at this frequency 3K, what the value of the signal. Okay, 5K, okay, and 7K, 7 harmonic. Okay, that only go into detail when you learning for RF radio frequency. Okay, same thing here. They just copy, okay, to display on the scope, display on the spectrum analyzer. Now we're talking about filter. Filters are circuits that are capable of passing signal with a certain selected frequency while rejecting signal with other frequency. This property equals selectivity. Okay, basically filter, they try to allow certain signal to pass through it, okay, and they block the other. And now you can see on your TV, on the cable, when they're coming in, they get a one wire and transmitted more signal for your voice for the picture, okay? So the voice will be the bandwidth for the voice from what to what?
20K?
From what to what? You have to get from what frequency to what frequency.
Oh, from 8 hertz to 20K.
Very close, from 10 hertz up to 20 kilo. Okay?
Okay.
And normally your voice will be 1 kilohertz. So when they go into the speaker, they need the low pass filter. Okay? They allow any signal from 10 hertz up to 20 kilohertz to go through it. And the other frequency for the picture will be at a high frequency. They will be go to the other filter to go to the display. So that's why I bring it up to make sure you understand the role of the filter, and they will be very depend what type of the filter. Okay, active filter we're using transistor op-amp combined with passive RC, RL, or RCL. Active device provide voltage gain, and the passive circuit provide frequency selectivity. They're telling you for the active filter, they get two parts. One, they're using op-amp to get the gain. Nothing to do with the frequency. However, the frequency will be defined by R and C and L. That's what the passive component. The active device provides voltage gain, and the passive circuit provides frequency selectivity. The four basic categories of active filter will be low pass, high pass filter, band pass filter, and band stop filter. Okay, first thing we're learning low pass filter. Low pass filter will be pass any signal less than cutoff frequency and higher than 0. Okay, but this is the ideal output. Response means output. Okay, and now it's practical here. Okay, this is the one they wanted. They want at the cutoff no more voltage. Okay, however, in reality, they still get the voltage here. Okay, and cutoff will be at minus 3 dB, and FC will be a cutoff frequency. Okay, and this will be 10 times of FC. So when you're looking into this output here, you must know this is the low pass filter output. Okay, the thing is that normally they asking you, they just given you that one, they asking you what is it. Okay, then you must answer will be this is a response or output of the low pass filter.
So Mr. Pham, that angle there, you have minus 3 dB equal to FC. So 10 FC is really minus 20 dB. Is that correct?
Right.
Okay,
depending on how many poles.
depending on what?
How many poles? Right here.
Oh, how many poles?
Right.
Okay, pole.
Okay, low pass filter, one pole. That means only one resistor and one capacitor. LPF, low pass filter, only allow low frequency signal from 0 Hz up to the cutoff frequency FC. Okay, point to pass while blocking dot any higher frequency. Cutoff frequency or corner frequency or critical frequency is calculated by FC equal 1 over 2 pi times RC. In this formula, joule times 3.14 joule, that pi. R will be in ohm. C have to be in farad right here. Okay, and F will be in hertz. At the cutoff frequency, the gain will be down minus 2 dB, or the output going down to 70.7%, same as 0.707 of its maximum value. After the FC, after the cutoff, output decrease at a constant rate at the frequency increase. That is, when the frequency increase tenfold, 1 decade, the voltage gain is divided by 10. In other words, the gain decrease 20 dB, okay, equal 20 log 10. Each time the frequency increase by 10. 1 pole LRPF, 1R, 1C, roll off rate will be minus 20 dB per decade. 2 pole, 2R, 2C, roll off rate 40 dB per decade. 3 pole, okay, 3R, 3C, roll off rate will be minus 60 dB. So we get a 1.2 pole, 3 pole. Which one is the best for now here?
3-pole.
3 pole. The thing is they cut it off quickly. Okay, that means after the cutoff, they don't want any more output. Okay, and this one just a picture giving you a little more a thing for your guy to see. Okay, so minus 3 dB here going down. This is the cutoff. Okay, and the bandwidth of the low pass filter will be 0 to FC. Okay, and after the cutoff, the gain going down. You see that? With the speed of the how many dB per decade. In this case, they say minus 20 dB per decade. A lot of people not quite understand what that means. That means after the FC, okay, decade means 10 times FC here. At this point, they will be going down 20 dB. Okay? There's a little more detail here. They given to you 3 different types of the low pass filter. There are 1 pole here, minus 20, 2 pole, minus 40, 3 pole. So basically, you don't want that one. The thing is, after the cutoff, they still get the voltage. Okay? This is close to what you want right here, ideal right here. Anything close to the ideal would be the best. Okay? Now, this one, then you need to know for me. For RPF circuit cell, R1K, C 0.1 microfarad, V in equal 10 volt IMS. Okay. Day one. Let's see. The gain. What is the gain for this op-amp circuit?
One.
Equal 1.
So,
You said equal 1, right?
yes, this is the following amplifier.
Perfect. They using it the follower. Okay. To build a low pass filter. Adding resistor capacitor here to make the low pass filter. But the op-amp is basically just the unity gain amplified. So the gain equal 1. Okay. Okay. The gain equal 1. See that? Now they want cutoff frequency. Who get the answer? Cutoff frequency equal FC equal 1 over 2 pi RC. At least you have to doing calculation. Make sure you get a right unit. Okay, who get it?
What's the value of R and C? Oh, okay. Yeah, I see it. I'm sorry, I see it. I see it.
Okay. You guys have to do it. Don't let Mr. Smith do it.
It's 1 over 2 pi times 1K times 0.1 microfarad.
1.591.
I had 1.57. Okay. Yeah.
Okay, if you're not doing your calculation, copy it. And you have to do some time. Then they want what V out at the cutoff. You understand, you can get it quickly, the answer. V in a 10 volt IMS.
It's 10 volt also.
Cannot be 10. The thing is at the cutoff, what happened? They going down 3 dB.
So it's 0.707
Yeah,
times.
7.07 volts.
That's correct. V out at 10 times FC. That means 1 decade.
To be 1 volt.
One volt IMS. If you're a little slower, then you have to get a copy and you have to redo it. Make sure you know why 7.07, why 1 volt, why 1.59K. If you done it, we go to the next one. Okay?
Next.
Now, on that one. For LPF, V in 2.5 volt IMS. They want to know what VO make VO at cutoff frequency, VO at 10 times of the cutoff. So you're looking on this circuitry here, you know what the configuration for this op-amp. What the name of this configuration?
Non-inverting amplifier,
Right, non-inverting. What is the gain?
RF over R1, which
No.
is
1,
1 plus.
right, R2 over R1. So V in 2.5, what V out? If you get the gain already.
On 25 VRMS, 25 volts.
V out, Mike, you said 25 volt. We'll see. AV equal 10.
Right.
FC 159 hertz. That means you have to using the formula 1 over R pi 2 pi RC. You see, they just adding 10K and a capacitor here to make the low pass filter. Okay. Anything calculation here just refer to the non-inverting. VL max 25 volt IMS. Okay, now you tell me what the VL at the cutoff frequency. You understand that really
17.675 volts.
16.66. That means 25 times 0.707.
Yeah, I got a different answer.
Yeah, I got 17.67.
That's what I got also.
So maybe I get a wrong one. Let's see. I do the calculation. That means maximum is 25, right?
Correct.
25 times 0.707. 17.675. Okay, I correct it right now. Oh man. Okay. Okay, I have to be answer, man, to correct that.
The last one was back to 2.5 volts at the end.
Yeah, let me correct that one. You tell me what the number here. 17.6
75.
675.
Yes, sir.
Okay, thank you. Okay, that's the on answer. Okay, next one. Active high pass filter. Okay, we try to done this part here. High pass filter pass any frequencies higher than the cutoff. You see that? Cutoff right here. Any frequency higher, they pass it. Any frequency less than cutoff, they will be attenuate or block it. Cutoff frequency formula is the same, 1 over 2 pi RC. Okay, now they given you that one. What the name of the op-amp? Unity gain. Gain equal 1. They adding capacitor, resistor, they just changing the position. Okay, if R here, C here, low pass, now C here, R here, high pass. So for the high pass, so they given you input 2 volt, R 910 ohm, C 0.1 microfarad. They want to calculate the gain, and you know the gain equal 1. Okay, and the cutoff frequency, tell me what the cutoff frequency.
1.75 kilohertz.
Okay, see what you get. 1.748K. Anyone get the same? Make sure R will be 910 ohm. C 0.1 microfarad. The lecture for the active filter is not too long. Okay. So next time we will be continue on this thing and also go to the other transistor will be a JFET transistor.
What they get for 3 and 4?
1.414. 2 ohm times 0.707. What will our FC divide 10?
0.2.
0.2. Okay, make sure you get copy for your answer. These are very basic circuitry. We have to know at least the formula how to do the calculation. I never seen in the interview they ask you to calculate it. They ask you the formula. Okay, any question up to this point? If you try to do your homework, you try to be in the Zoom every time, I can guarantee after this semester you get a very, very good basic in the electronic.
Mr. Pham, like for when they say the filter bandwidth, does that mean, is it the same as when you say the cutoff frequency? So is the cutoff frequency is the filter's bandwidth?
Yeah, that means bandwidth will be going, from the cutoff frequency. So the bandwidth in here will be from FC up to infinity here. We don't care. You see that? However, after the cutoff, they will be attenuate, okay? They will be reduced. They opposite to the low pass filter. Low pass, they pass low frequency. High pass, they pass high frequency. Okay?
Okay. Thank you.
Yeah, they get about one pass, low pass, band pass, and band stop band. That means they cover every signal can be allowed to pass or not allowed to pass. Okay? So if you don't have any more questions, we stop here.
Yeah, well, I meant page 10 and 11 on this active filter, because I was having problems here. Because I got some of the answers down, I just didn't get all of them.
Okay, you mean the calculation here?
Yeah, you're on page 12 now. I just need to go back to page 10 and 11.
Which one did you got?
Okay, go back to page 10 or 11, please.
Page 10?
Yes.
That's 11. Okay. Page 10. This is a low pass filter. So what's your question?
He was looking for additional information.
You can see they just changing position C and R to make low pass or high pass. C on this side, R on the other side will be high. Okay? On this side, R here, C here will be low. Easy to recognize. And that will be only one pole, one R, one C. Two pole will be two R, two C.
Hey, Mr. Fan, how come on this on the little graph there, it's got 10 FC 3 times? What are they saying? Or should that be 10, 20, 40, or?
No. They given you three, but think a different pole. That means on that guy here will be minus 20 dB one pole.
Mhm.
However, the same 10 times, but this signal will be for two pole. That means more pole they will be going close to the ideal right here. That's only telling you if the 3 pole is the best on this display.
But on the bottom where they got like the 10 FCs, shouldn't those be like
That means they're supposed to draw 3 different. Okay?
Okay.
That's the same for decade. 1 decade, okay, here for 3 pole. And if the depth, decade here for 2, and a decade here for 1, they compare between a different pole, telling you which one is the good one.
So the 60, the bigger the pole, the better?
That's right. They very
Okay.
close. This is the one you want right here. FC right here.
Mm-hmm.
That means ideal. They cut off right away. No more.
Right.
Okay.
But we don't get the ideal And so the better one in this particular graph is minus 60 dB.
That's right.
Okay, thank you.
And that greater attenuation rate
Right.
basically represents a greater selectivity for your circuit or for your signal that you do want.
Exactly.
Now, Mr. Fan, on this example, it was asking 10 FC. So how do we get that? Because
If you get a frequency cut off 1K, 10 FC means 10 kilohertz.
say that again, I didn't quite get that.
If I said the cutoff frequency is supposed to be 1 kilohertz, then 10 FC means 10 kilohertz.
Okay. So what's the voltage out at the?
Depend on which one. If you're talking about
On this example here, if you click it, I think your answer comes up.
okay,
The question come up, yeah. So what I'm saying is number 4, V out at 10 FC
okay,
equal to 1 volt.
okay. V out at cut off will be
Yes.
now 3 dB. Right?
Mhm.
3 dB means 0.707.
Correct, yes.
So you get out. The voltage will be 10 volt IMF.
Mhm.
So they going down to 0.707 of 10.
Right, that I get. Now, what about the next one? V out at 10 FC.
10 FC mean 0.1. The thing is you cannot calculate with the del dB. You must be calculate with a number.
Right.
Okay? 10 times of FC, they will be going to 0.1.
For 1 pole, that is, right?
That's why 1. 10,
So 0.1 times 10.
right,
And 0.1 is for 1 pole. Is that correct?
right.
Okay, got it.
Okay? So we will get more next meeting.
Thank you, Mr. Pham.
Yeah, no problem. Okay? To me, you guys have a good weekend, okay?
Thank you, Pham.
Thank you, Mr. Pham.
Thank
See you
you.
tomorrow, Mr. Pham.
Yeah, see Mr. Smith tomorrow.